For this video, we are going to talk about the zeros of a polynomial function. Basically, the zeros of a polynomial function are the values of x that will make our polynomial function equal to 0. Usually, zeros and roots are often be compared. Why? Because the process of getting the roots of a polynomial equation and the zeros of a polynomial function is or just the same. So let's compare the two. So again, in polynomial equations, we solve for the roots. This only means that if we are talking about the roots, it means that we are dealing with polynomial equations. Zeros are for polynomial functions. So when we talk about zeros, it means that we are dealing with polynomial functions. So as defined a while ago, this are value or values of x that will make the function p of x, f of x, g of x, or whatever the polynomial function name is, it will make equal to 0. Now, graphically, zeros can be seen as the x-intercepts of the polynomial function. So in short, if we're looking for the zeros of the polynomial function, as well as we're trying to graph the polynomial function, we can already identify some distinct points in its graph, which are the x-intercepts of the polynomial function. Thus, if p of x has zeros r sub 1, r sub 2, until r sub n, the graph of p of x has x-intercepts r sub 1, 0, r sub 2, 0, until r sub n, 0. So, why did I represent r sub 1, r sub 2, until r sub n as zeros of the polynomial function p of x? Because when we solve for the zeros of the polynomial function, look at this. We let p of x, or the function itself, be equal to 0. So, for example, if it's represented as p of x, f of x, g of x, so you replace that with 0. So what will happen to the given polynomial function? It becomes an equation. Now, you want to find the value or values of x to make it equal to 0. But what can you see in the given expression when you try to replace f of x and g of x or p of x as 0? It becomes an equation. So, technically, you are just simply looking for the roots of that polynomial equation. So, that is why, in the previous slide, I just renamed the zeros of the polynomial function p of x as r sub 1, r sub 2, until r sub n. Alright, so what are the useful concepts to help us get the zeros of the polynomial function? First is the rational root theorem. Yes, we're going to use the rational root theorem to get the zeros of the polynomial function. But in other books, they try to replace the rational root theorem because it's all about, when we talk about rational root theorem, we're talking about polynomial function. So sometimes they named it as rational zero theorem. But the concept is just the same. You get the factors of the constant term and you get the factors of the leading coefficient. And then you get the ratio or possible combinations of the factors of the constant term and the leading coefficient. And these are the possible rational zeros of a polynomial function. Then, what else? We also have the Descartes rule of sign. Let me just put a apostrophe mark here. Okay. Now, what is Descartes' rule of signs? Actually, before you use the rational zero theorem, you can use the Descartes' rule of signs. Why? Because the Descartes' rule of signs is used to determine the number of real zeros of a polynomial function. So, please take note, I will highlight real zeros. When we talk about real zeros, meaning we can have a rational or irrational zeros. Okay? So when we try to determine the real zeros of a polynomial function, it will also give us an idea of how many imaginary zeros are there in this polynomial function also. But why do we have to find, or why do we have to determine the number of real zeros in the polynomial function? It's because it will help us how many x-intercepts can we have in the graph of a polynomial function. Because imaginary number, we cannot graph, okay? We cannot graph an imaginary zero in a real number line or in a Cartesian plane. This is why we only have to determine the real zeros of a polynomial function. So how does Descartes' rule of sign works? It tells us the number of positive real zeros in a polynomial function f of x is the same or less than by an even number as the number of changes in the sign of the coefficient. The number of negative real zeros of the f of x is the same as the number of changes in sign of the coefficients of the terms of f of negative x, or less than this by an even number. So in short, when we look for positive real zeros, we just have to get the alternating signs of f of x, no, the terms or the coefficients of each term in f of x. If we want to get the negative real zeros, we just change f of x to f of negative x, meaning we substitute negative x to all the x's of f of x, then determine the number of alternating signs in each coefficient, and this will give us the number of negative real zeros. Then, to find other combinations, we can just simply subtract even number. Okay? We can subtract an even number to the number of positive real zeros or to the number of negative real zeros. So, in this case, we have to find all possible combinations of real, positive real, and negative real in each polynomial function. So, let me present an example. Okay, f of x is equal to x cubed minus 4x squared minus 3x plus 6. So, let us check, no? What are we going to do first? Before we check the alternating sign, make sure that our polynomial function is written in standard form. When we say standard form, the terms must be written in decreasing order. So the exponents of x must be decreasing to say or to determine that our polynomial function is written in standard form. Aside from that, we also have to check if our polynomial function contains a constant term. Because if it does not contain a constant term, this only means that one of the zeros of a polynomial function is or are 0 depending on its multiplicity. And we know that 0 is neither positive nor negative. So, fortunately, in our example, we have a constant term, so it won't be a problem now at this moment. Okay? And we know that this particular function is already written in standard form. So all we have to do is to check the sign of each terms. So this is positive, this is negative, and this is positive. So this is the sign for f of x. Okay, then let us count the alternating signs. So if the two coefficients are alternating, okay, it means that there is a change of sign. So we have your positive, negative. So this is counted as one change in sign. Negative, negative, so they are both negative, so there's no change. Negative, positive, so they are different again or opposite sign, so another change of sign. So how many change of sign do we have here? We have 2. And since we have, or we're talking about f of x here, so meaning this is the maximum number of positive real roots. Okay? Maximum. So that's 2. Now, how will I get the other possible number of positive real roots? I can subtract this number by an even number, as long as it will not be equal to a negative number. So, 2, I can subtract 2 from it, okay? Since 2 is an even number, so 2 minus 2, it's 0. So, I can also have no positive real roots at all. Now, how am I going to determine the negative roots? So, what do? We get f of negative x. So, what would be the new value when I use f of negative x? So, negative x cubed, so that becomes negative x cubed, x squared, so that's positive, x squared times negative 4, so that is negative 4x squared, 3x, so 3 times negative x, so that's negative, times negative here, so that becomes positive, and then there's no x, so plus 6. Then, let's check the sign. So, for f of negative x, we have your negative, negative, positive, and positive. So, negative, negative, no change. Negative, positive, there's a change, so that's counted as 1. Positive, positive, there's no change. So, we only have one maximum, okay, possible negative real root. Okay, so remember, when we're talking about real roots, we also have to consider the, what do you call that? We also have to consider the irrational roots. So we have here 1. Of course, you have 0, you also have 1. You cannot subtract an even number here because it will give you a negative value already. So that's the only possible number of negative value or negative real root that you can have. Now, how will I get the number of possible imaginary roots? So the total number of zeros of a certain function will also depend on the degree of the function. So, what's the degree of this function? We know that the degree of this function is 3. So, the total number of roots of this particular function f of x must be 3. Then, you check each row. So, 2 and 1, when you add all of this is already equal to 3. So, that leaves us in this row, in this possible combination, that leaves us no imaginary roots. Now, how about this one? No positive, 1 negative. So, I have 3 total. So, it means that in this combination, I still have 2 imaginary roots. So, this is a combination, and this is another combination of real roots and imaginary roots of the function f of x. Okay, then after getting the combinations of positive and negative real roots as well as the imaginary roots, we can now solve for the possible, or no, not possible, but we can now solve for the zeros of this particular function. So, how are we going to find the zeros of this particular function? First, we let f of x equal to 0. So this becomes 0 is equal to x cubed minus 4x squared minus 3x plus 6. Then solve for the values of x. So in short, we're just solving for the roots of this particular function. So we have to use the rational root theorem, or in this case, since we're talking about polynomial function, we have to use the rational zero theorem to get the possible zeros. Possible zeros which are possible rational zeros of this particular function. So what are those? So since our leading coefficient is 1, so we only have to deal with the factors of 6, or the factors of the constant term. So we will have plus or minus 1, plus or minus 2, and plus or minus 3. So these are the possible rational zeros of this equation. Then, what are we gonna do next? Let us try if we can have, let us look for the rational zeros of this particular equation by simply dividing them using continuous division. So, let's start with 1. So, that would be x cubed negative 4x squared minus 3x, then plus 6. So I'm going to use the synthetic division to verify. So this is 1. This is 1 times 1, 1, negative 3. Negative 3 times 1, negative 3. Negative 6, negative 6 times 1, negative 6. So 6 plus negative 6, that's equal to 0. So in this case, we have 1 as one of the zeros of this particular function. So how am I going to get the other 2 zeros? So I will just simply change this particular expression here into quadratic expression or quadratic equation. So that would be x squared minus 3x minus 6 equals 0. Then use the quadratic formula to solve for the other zeros of this particular function. So that would be negative b plus or minus the square root of b squared minus 4ac all over 2a. So therefore, it's negative 3 plus or minus square root of 9 plus 24 all over 2. So this is 3 plus or minus square root of 33 over 2. So we know that this is a real number. So that would be 3 plus square root of 33 over 2 and 3 minus square root of 33 over 2. Okay, so let's take a look at the zeros of our function. So 1 is a positive real root. Okay? As well as 3 plus square root of 33 over 2. It's obviously a positive real root. So you have 2 real roots. Why? Because the second one is a negative real root. Why did I say so? Because square root of 33 is obviously bigger than 3. So it results to a negative real root. So looking back at our Descartes rule of sign a while ago, combination 1 satisfies the zeros that we got from this particular function. Alright? So let's have some more examples using the Descartes rule of sign. Now, I have here f of x is equal to x to the 6th plus 2x to the 5th minus 10x cubed minus 6x squared plus 3x minus 8. So, in this case, I have to look for the positive real root, the maximum number of positive real root of this particular function. So, x to the 6th is positive, x to the 5th is positive, then look at this. There are some missing term, which is the value x to the fourth. Just disregard the missing term. Okay? So we just have to list the coefficients that has a certain sign. So, positive, positive, negative, negative, positive, negative. So, I already checked. It is already in standard form. And there is a constant term. So, I just listed it. Okay? So, now, let us check the change of signs or the alternating signs of f of x. So, we have 1. We have 2. And 3. So, there are 3, what? Maximum of 3 positive real roots. So, I will write here 3. Okay? Then, I can subtract an even number from 3, which is 2. So, I'll subtract 3 from 2. So, I can subtract any even number as long as it will not give me a negative number. No? So, 3 minus 2, that's equal to 1. Okay? So, you can also have only one positive real root. Now, how about for negative? F of negative x. So, that is x to the 6th minus 2x to the 5th plus 10x cubed minus 6x squared minus 3x minus 8. So, f of negative x is positive, negative, positive, negative, negative, negative. So, let's count. 1, 2, and 3. So, there are a maximum of 3 negative real roots. So, I can have 3 in 1. I can have 3 positive and 3 negative. Yeah, tama. 3 positive and 3 negative. 1 positive and 3 negative. Now, aside from having 3 negative real roots, I can also subtract it to to an even number, which is 2. And the result is still a positive number, which is 1. Okay, now what will I write to the positive number? I will just simply copy 3 and 1. Okay, then place 1 2 times. In short, if I have a maximum number of 3 real roots, this means that I have 3 or let me erase this. Okay, I can have 3 or 1 negative real root. And this one, since I have 3, I can also have 3 or 1 positive real roots. So, if I have 2 possible numbers here and 2 possible numbers here, what are the possible number of combinations that I could have? So, of course, I can have 4 possible combinations. That's 3 positive, 3 negative, 1 negative, 3 negative, 3 positive, 1 negative, and 1 negative, 1 negative. Okay? Next, how am I going to determine the number of imaginary roots? So first, determine the number of total number of zeros that we can have for this one. So we have 6. So all of that must have 6 zeros. Okay. So I have 3 positive, 3 negative. When I add them, it will give me a total of 6 zeros already. So this leaves me no imaginary number for this combination. 1 positive, 3 negative, so that's 4. but I need to have a 6 0, so that gives me 2 imaginary real roots for this combination. Another 2 imaginary imaginary roots for this combination, for the third combination, and 1 positive, 1 negative, so that gives me 2 real roots. So, meaning the imaginary roots of this combination must be equal to 4. Okay? And these are all the possible combinations of real roots and imaginary roots of this particular equation. Descartes' rule of sign is just a simple concept, but of course, we also have to check if we have already exhausted all the possible combinations of the number of positive real roots and negative real roots that we could have. So another reminder is that we always have to make sure that the expression on the function that you are checking has a constant term. Having no constant term in the function means we have 0 as 0 or zeros of the function, and 0 is a real number. But it is neither a positive nor a negative real root. For example, f of x is equal to x cubed minus x. So in this particular function, there's no constant term. So if we try to factor this is x times x cubed minus 1. X means that there is a factor, or there is a 0 that is equal to 0. No? Because, in short, I can have the value 0 here as the zeros of this function. So how will I determine this particular equation? No, sorry, this is x squared. Okay, x squared minus 1. So how am I going to determine the other possible positive real roots and negative real roots in this equation? So, ang gagawin natin, we will just simply omit this part here, and we will only get the number of real roots using this particular equation. So let's say this is f prime x squared minus 1. So just look for it, your positive, negative real root, imaginary, and then total. So look at this. This is positive, this is negative. So for positive real root, you have 1. Negative real root, f prime of x. So that's x squared minus 1 also. F prime of negative x. This is negative. Oops, let me write it again. F prime of negative x. There. So it's still x squared minus 1. So I have 1 for negative. I have a total of 2 roots in x squared minus 1. So that leaves us no imaginary root. So I cannot subtract this one by an even number. So this is the only possible combination that I could have for this particular example. Okay? So I have 1 positive real root, 1 negative real root, and 1 0 as the zeros of this particular given function. Now, I have here some exercise. This is exercise number 1. I want you to use the Descartes rule of sign. So answer it in a piece of paper